All right, guys, what we're going to be looking at here, as you're aware, is we're looking at the review for the Fundamental Theorem of Calculus test. Now, just like on a lot of the other reviews, a lot of the work has already been done on these problems. The ones that haven't been done, I'll take a little bit more time to go through just to make sure that you understand. So, to start off with, if you remember, when we're looking at all of these problems that deal with a limit as n approaches infinity, these summations that we have, what you're going to do every single time is you're going to say, okay, the integral starts at this number right here. And then it's also the interval is going to be whatever number is on top of both of those fractions. So it's going to start at 2. Since both of those numbers are 3, that's how big the interval is going to be. So it's going to end at 5. And then we know the function is x squared in this case because the whole parentheses is being squared. And if you remember, the 3 divided by n on the end is our dx. So there are all three of those answers. Hopefully, again, that kind of makes sense. And if you need to pause it for just a second to check your work, that's totally fine. But those are those three answers right there. I believe all three of them. Yep, looks good. All three of those are correct. Okay. So when we're asked to evaluate a definite integral, don't forget what that means. There's three steps, to evaluating every definite integral. We look at the function in question. Because really what this is asking is I want to know, like looking at this graph. So I've got y equals 3x here. There's my graph. And I want to know what the area is from x equals 0 to x equals 2. So that is what we're looking for. And I'm not going to draw that on the other ones. But the way that we do that is we take the antiderivative of our function. So that's what the 3x squared divided by 2 is. Then we evaluate that function at the number on top first, then the number on bottom. Remember, it's always top minus bottom. That's one of the mistakes that I see an awful lot. Once you do that, then you subtract top minus bottom. So number 4, you get 6. Now don't forget 1 over x, the antiderivative of that is the ln of the absolute value of x. One other mistake that I want to make sure that you avoid making is when you have a function like we have here on number 6, I want to make sure that you understand that we are subtracting that entire number. So all of this stuff after the minus, I would recommend finding out what that number is first and then subtracting that rather than subtracting each individual thing. You can do it either way, but it's much more difficult when you subtract one thing at a time. The other thing I will say is make sure that whenever you plug in your top or bottom number, you're using parentheses, especially with negative numbers, so you don't make mistakes on what the sign should be once you carry that out. On number 7, this is about the only other one. Well, there's a couple things I want to talk about here. You look at this, you're like, I don't know how to take the antiderivative of that. When we look at this problem, and I see it, first of all, I say, okay, I don't know exactly what's going on here, but one thing that we can look at is we can realize that the bottom here factors down to x minus 4 times x plus 4. If we cross out the x minus 4s, we're left with 1 over x plus 4, which those two graphs look identical other than there's a hole in the graph at x equals positive 4 on this function if that's what we're looking at. Nothing we need to worry about because that's where our interval ends. So we're continuous and differentiable on the interval in question. Then we just take the antiderivative, and you can see that here, and you get a decimal number. Now, on number 8, we have to realize that when we take the antiderivative of cosine, we do get sine, but the inside part stays the same. And then remember, we divide by the derivative of what is on the inside of the parentheses, if that is a linear function, which is what we have here. So I take that, and then I just evaluate it, and I get 0. Now, that doesn't mean, all that means basically is my cosine graph has the same amount of area above the x-axis as it does below on the interval in question from 0 to pi, so that area cancels out. On number 9, very similar, I've got e to the negative 2x. So when I take the antiderivative of that, it is e to the negative 2x, and then we divide by, again, the derivative of what is in the parentheses. So that's how we get the answer to number 9. So there's the first 9 there. Now, number 10, we want to set up these problems, but not evaluate them. So in other words, I'm going to choose my u. So I get u equals, on number 10, x to the third plus 2. So I've got that du dx is equal to 3x squared. I get the dx all by itself, so I get dx equals du over 3x squared. And then what I do is I plug that in for dx. So I'm going to get the integral from 0 to 1 of x squared times u to the 5th times du over 3x squared. I see the x squareds cancel, and then 3 is a constant number that we're dividing by, so we can move that out in front of the integral. And I get 1/3 times the integral from 0 to 1 of u to the 5th du. Now we're not done yet, because what we need to do, we have to write everything in terms of u, including the limits on our integral. The way that we do that is we just take those two numbers and we plug them into what u is equal to. So I've got u is equal to, the first number is 1, so I get 1 cubed plus 2. 1 cubed is 1 plus 2 is 3, so this changes to a 3. When I plug 0 in, 0 to the third is 0 plus 2 is 2, so 0 to the third plus 2 is 2. So 2 is what goes on the bottom, and that is our answer. We don't need to integrate that. Now I'm going to pause it for just a second and write out the other two answers just so you can check your work. They work very similarly, so hold on just a sec. All right, so just a couple things that, now that the answers are here, a couple things that I want to call your attention to. First of all, I know it's kind of weird that the number on top of number 11 is so big, but when I use my u substitution on that one, I get 3 times 3 to the 5th. 3 to the 5th was 243 times 3 more is 729, and that's just how that number comes out. I know it's really big, but sometimes they just work like that. On number 12, the thing that I want you to remember is sine squared of x is the same as sine of x squared. So our u is going to equal sine of x. So our final answer down here, after we do everything, is the integral from 0 to 1 of u squared du. And hopefully that kind of makes sense. Now on number 13, what we have to do, there's a couple ways to think about this. In reality, this is a square. And you can see that the area that I'm looking for is just half of that square. It's an assumption that you can probably make. So the area of this square, it's too tall and it's pi wide, so it's 2 pi, so half of that is equal to 2. Now another way to think about that is the entire area of this, it's not a square, it's a rectangle. The entire area of that rectangle is 2 pi. If I wanted to subtract off the integral from 0 to pi of that function right there, I could do that as well. And when I would, if that's not 2 pi, that's pi. Or not 2, that's pi. Jeez, Parker. Okay, you would find out that this answer is pi as well. Either way you want to do it, what we have to realize again is the integral tells us this area right here. And then, but that's not the area I'm looking for. I'm looking for that shaded region. I know on your worksheet it's not blue, but that's the shaded region that I'm looking for. That, unfortunately, is not what the integral tells us, but we can find that by subtracting off that area. Number 14 is a little bit more difficult, just because on number 14, we have to look at 3 separate things. The first thing that I need to look at is this rectangle right there. So that rectangle, the area of that rectangle, there's a base of pi over 4, and then it's square root of 2 tall. Now I know that looks bad, but that's the area of this rectangle right there. Now what we do for the rest of this, I know those thetas look weird, they're just like x's. What we're going to do next is we're going to do the integral from negative pi fourths to 0 of secant theta tangent theta. Now I actually don't care too much if you use your calculator on these. So that'll tell us now we found this area down here. So that's my second area. The last thing I need to do is find this shaded region over here that I've got kind of swirls in. Okay. So what I need to do for that is I've got another rectangle, which is pi fourths divided by 2, or times the square root of 2. Technically, again, just like we looked at on the previous problem, that is half of the area. But if you wanted to look at it a little bit more technically, I could subtract off the integral from 0 to pi fourths of that same function. Now the way that we type, just so you're aware, the way that you type secant into your calculator is 1 divided by cosine. So if you want to, and I'm going to just, I forgot to plug it in, so let me plug this in real fast. And what I got when I plugged that in is I got 1.807 for that total area that we have there. Technically, if you wanted to go with the really big rectangle, it is half of that area as well. Be careful when doing that though, that one's a little bit harder to see, but you could have looked at it that way as well. Now, on these, we're just using some of the rules that on 15, 16, 17, and 18, and I know those are mislabeled on your review, but on 15, 16, 17, and 18, we're just using the rules that we've talked about before. So if I want the integral from 6 to 1, that is the same as the negative version of the integral from 1 to 6 of f of x dx. Well, you'll notice I've got the integral from 1 to 3 is -4. The integral from 3 to 6 is 5. So if I want the integral from 1 to 6 of f of x, what I can do is I can just go -4 plus 5, which is 1. So that entire integral is 1, but I'm not looking for the integral from 1 to 6. I'm originally looking for the integral from 6 to 1. So my answer for number 15 would be -1. On number 16, remember, one of the rules we have is the constant multiple rule. So I can move the 3 out in front, and then I've got the integral from 1 to 6 of g of x dx. So I know what that is. It's written right there. 3 times 9 is equal to 27. And there's your answer for number 16. Okay, so on number 17, we're doing the integral from 1 to 6 of f of x plus g of x. Now the rule that I want to focus on here is technically, and it's not really distributing, but you can find these areas individually and then add them together. It's just one of the rules that we talked about. So the integral from 1 to 6, we already found that that was positive 1. The integral from 1 to 6 is 9, so 1 plus 9 is equal to 10. Number 18 combines two things together. We've got the constant multiple rule, then we've got the order of integration rule, because right now I'm going from 6 to 3. I need that to go from 3 to 6, so I can technically move the negative out in front, and that makes it look like this. Once I've done that, then -2 times -1 is 2. The integral from 3 to 6 is 5, so 2 times 5, we get 10 again for the answer. So again, hopefully that makes sense on number 18. Now on number 19, 20, and 21, what we're basically saying is, okay, look at the interval in question, and then the second part of the fundamental theorem of calculus does not work if the function is not continuous or differentiable, or honestly, if that function doesn't exist on the interval in question. So on the first one, I have a vertical asymptote at x equals -3. Since I have a vertical asymptote at x equals -3, oops, and this one actually, we can use this is a mistake, but I meant to write x minus 3. If it said x minus 3, we would be at x equals 3. And then we would say, okay, 3 is between 2 and 5, so it's not continuous at x equals 3. But that's a mistake there, so oops. On number 20, I've got x minus 2 times x plus 2. That, on this one, this is correct. At x equals 2, you'll notice 2 is between -2 and +3. So I am not continuous. I have myself an asymptote at x equals 2. On the last one, you might say at first, well, the ln of x, I don't remember real well what that graph looks like. That graph looks like this. The problem for the ln of x is it starts existing just barely to the right of x equals 0. This is an integral going from -2 to +2, so I can't do that because I can't find any area over here. So most of those are either it does not exist. Again, I screwed up on number 19 and I apologize. And then number 20, there is an asymptote there. Okay. Numbers 22, 23, and 24. Remember, the first part of the fundamental theorem of calculus, when we're looking for a derivative, if it's just from a constant number to x, we just replace the t with x and we're good in the hood. So on number 22, that's the same. Now on number 23, I realize that's just a constant number, so it just stays the same. Okay, and there's no x, there's no t to replace the x with, so I just leave it like that. Now, number 24, it changes a little bit because we're not going to x, we're going to 2x. Really, the only thing that changes is we've got the sine of 2x, the cosine of 2x, and then we multiply that by 2. So that is what our answer is on number 24. Here's 25, 26, and 27. So 25, don't forget, in order to get the x to the top, we need to make the whole thing negative, or the x squared to the top, we need to make the whole thing negative. So we do that, it makes the whole answer negative, and then I'm multiplying by the derivative of x squared at the end. When we have an x on the top and the bottom, what we do is we just plug it into the top first, like we normally would. Then we plug it into the bottom, whatever the bottom is, we plug that in, and then we subtract them. Okay? Hopefully you got all those answers right. I know 27 looks a little bit complicated, but it's nothing to be overly concerned about. So here, this is if all of these make sense, you should be fine on the test. If you have any questions about any of this, then please let me know.